Thomas Garcin. I'm a research team leader at the University of British Columbia. I've worked with a global system equipped with a LUMET for the past 3 years. It is my pleasure to introduce this system to you today and to describe the basic principle of this technology and its application. LUMET system stands for Laser Ultrasonic Sensor for in-situ metallurgical processes. So what we want to do with this system is that we want to be able to monitor in real time different sorts of metallurgical phenomena and different sorts of metallurgical parameters. So some of them are listed here. There is like the possibility to sense recrystallization, the possibility to monitor in real time phase transition, to capture the variation in grain size in materials, and of course get an idea on the texture in material. So before going into more detail on the principle of the technique, I'd like just to show you how it looks like. So here is a picture of a laboratory in UBC in which the first system has been installed. And so you recognize here, highlighted in red, is the global system. So there is the different component of the global machine that has been designed and developed by the company DSI. And this LUMET system here is made up of two basic components. The cabinet here, the white cabinet here, contains the optics and electronics for the system. And attached to this cabinet, there is what we call a probe that contains lasers and which is attached to the rear door of the global chamber. So it's going to fire some laser onto a sample. And so as you see here, it's all enclosed, and so a material scientist, which has no knowledge about lasers, is able to do a measurement with LUMET and does not need to wear any laser safety goggles and things like this. All of this system can be controlled on a control table, which is on the back of this slide over here, as all this software that is developed in DSI has been coupled with the software with LUMET, so to have the possibility to interact directly with both equipment simultaneously. We are going to go a bit closer to the sample, and we are now inside the chamber of the global machine, where we have the conventional jaw of the global machine. Here is the pocket jaw, where we have a sample inside, which is red because it's at very high temperature. And so the interesting things about this LUMET system, it is coupled to the normal jaws of the global machine, which has been validated for all sorts of testing. The only requirement for this LUMET system is that one side of the sample should remain free for the laser to fire at its center. Then we are going to go even closer to the material and look at what's inside the material. This material here, inside here, contains a multiple number of grains. All those grains are called crystals, and each of them have a different crystallographic orientation. So it's represented here as some grains like that. And what we see here, it's a plate where we have some lasers that fires onto the sample. And so there is two lasers. There is one first laser which has a very short duration, and this laser is going to vaporize a little layer of the sample. And this evaporation of ions of metal is going to form a plasma, and this plasma is going to evaporate very rapidly out of the surface of the sample. And this very rapid evaporation is going to create a pressure wave inside the material that will propagate perpendicular to the surface of the sample. This pressure wave here, represented in red, is going to bounce back and forth between the two surfaces of the sample. And there is a second laser which is looking at the sample, and each time this wave comes back at this generation surface, there will be a tiny microscopic displacement that will polarize the light of this detection laser. This light reflected on the sample is collected in the probe, and thanks to an interferometer, we can access to a signal which is proportional to the surface displacement measured here at the generation surface. Of course, there is a possibility to have the thermocouple on the other side and potentially measure the dilatation simultaneously if we wish. So then we are going to go even closer and look inside this material. And to do that, we have here a picture where we have some grains that is a steel which contains numbers of grains and had various shapes and various morphology. And thanks to a computer simulation, we can look at how this ultrasound wave or elastic wave propagates and bounces back and forth in between the two surfaces of the sample. So you see that at the beginning it remains fairly plain, and then quickly after a short moment it occupies the whole volume of the sample and continues to resonate inside that sample. So now let's see what is this signal that we have to deal with and what type of analysis we can do and parameters that we can measure. So each time this wave comes back at the generation surface, we will measure a little surface displacement, which is called an echo. So when the echo comes back the first time, we have the first echo, second time the second echo, and so on. Each time the echo comes back, you see that its amplitude is decreased because the energy of the wave has been spread in various directions as the wave propagated through the sample. So there is two important parameters that we are going to systematically calculate. The very first one is the speed of this wave, the velocity. The speed of this wave is directly proportional to the time in between two echoes and related, of course, to the propagation distance, that is the thickness of the sample. This accuracy, this parameter, the velocity, is measured with a very, very great accuracy thanks to complex algorithm, and we can then monitor very small changes in the bulk elastic property of a material. The second important parameter is this decay, or called attenuation, is how much energy has been dispersed through a sample during a certain propagation distance. This attenuation is particularly interesting because it's going to be proportional to the size of the grain. If the grains or crystals are very large, the attenuation will be very large. If the grains are small, the attenuation will be small. And so thanks to some correlation that we can make ex situ, we can then directly quantify the value of this average grain size by measuring this parameter, the attenuation. So now I'd like to show what is the basic principle of grain size measurement with Lumet. And so, of course, you have to do the experiment in the global machine. You capture this raw signal, which is the second step. And then the important things, once you have measured the attenuation, is to build what we call the calibration. That is that using this attenuation value that you have measured, you can then correlate this with a grain size that you can measure ex situ. Using an optical metallography in a sample in which you know the grain size, you can relate this attenuation value to a grain size that you know. And this has been done for austenite in steel, for instance, and it's very easy to develop new calibration for other type of material, other phases, but the principle is always the same. Once we have this calibration, it is possible to get an absolute value of grain size. By simply now measuring the attenuation, we can then know how the grain size varies during a certain treatment. So let's look at example. And so one of the breakthrough of this system was really to measure the austenite grain size in steel, because in steel this austenite phase is only stable in the very high temperature domain, and as you cool down the alloy, this austenite phase transforms into other transformation product, and it's impossible to measure this grain size. However, the size of those austenite grains is very much related to the final mechanical property of the material, and every steel company needs to control this grain size very accurately during what we call the hot rolling process. So thanks to Lumet, it's now possible to acquire the change in this grain size during isothermal holding here, where we have here the red curves are the values of grain size measured with Lumet, and those points here, which relates very well with Lumet measurements, are verification of those grain size. During continuous heating here, this is another example where we can discriminate between a steel that contains some precipitate, in which the growth of those grains is very slow, it's the blue curve here, and a steel which does not contain precipitate, in which those grains grow fairly rapidly here. So it's to tell about the sensitivity of such a device. So this important to remember is that this grain size measurement is made from the measurement of the attenuation. Now I'd like to make use of this additional value is the velocity. And so the velocity is going to be telling us a little bit about how the bulk elastic properties are changing during a treatment. And what we see on this graphic here is the variation of the velocity with respect to the temperature as we heat up a steel plate. So upon heating, the velocity is changing non-linearly because this steel has some magnetic properties. And then as we are going into this phase called austenite, at high temperature, the velocity is going to be much lower. As the steel is being cooled down, the austenite will retransform into ferrite, and we can monitor this upon cooling thanks to this curve. And in a little bit the same way as we do with dilatometry, we can quantify the cinetic of this transformation from austenite to ferrite using what we call a Lover rule. And so what we see here is a direct comparison between a Lumet measurement of this phase transformation and a dilatometry measurement. I'd like to attract your attention that this type of measurement can be done during a very high cooling rate. Here this measurement is done at 100 degrees per second, and this is possible thanks to the fact that Lumet can generate up to 50 pulses per second. So now I'd like to show you an additional example of use of velocity. It's called monitoring of a phenomena called recrystallization. It's a very important phenomena, as very often we need to make a steel stronger by a process called cold rolling. So a cold rolling structure would look like the one on the top here, where all the grains are elongated in the direction of rolling, and the structure is highly deformed. However, such a structure is sometimes a little bit brittle, and so what we want to do is reheat it to a certain temperature to do what we call a recrystallization. Recrystallization is a phenomena which would replace this structure by a new family of grain, which all will have a new crystallographic orientation. And so you see here this structure after the recrystallization. The grains are now polygonal and they are not deformed anymore. This transition from this structure to this structure will be associated to an important variation in the bulk elastic property of the material. And so of course, because Lumet can capture those changes, we can see here during a first annealing, as the structure changed from this state to this state, an important variation in this velocity value here in blue. And then when we would take this structure and re-anneal it, nothing will happen in this structure, and we prove that nothing happened in this structure. So here again, this is a technique that can capture in real time and very, very quickly the entire kinetic of this recrystallization process. Now, a final example, and I think to me one of the most interesting examples, as most of the industrials are interested about hot rolling process and how the microstructure evolved during hot rolling process. I have here an illustration of how the system Glibol can be helpful to study those phenomena, and how Lumet can actually help to understand better what's going on inside this microstructure during the treatment. We have a quenching nozzle here, a contact dilatometer, and this is the usual ISO-T assembly that the Glibol has validated for many years for uniaxial compression experiment. And what you see here, it's a video where we have the sample being deformed and the laser shot firing 50 times per second on the sample. And so what I'd like to show you now is like how those two parameters, the velocity and the attenuations, are varying during these things. So what we have to see is that depending on the rapidity at which you deform this material, the speed or the strain rate, the phenomena occurring in the microstructure will vary. And so what we see in this last slide here is first here is the commotional stress flow curve, where we have the stress plotted on the y-axis and the strain on the x-axis. And we have here a very low strain rate and gradually increasing the strain rate. What you see here, there is a broad maxima, and then the flow stress decreases, which is very much responsible, very much associated to a phenomenon called dynamic recrystallization. It's a recrystallization as we saw before, but this time happening during the deformation. And this dynamic recrystallization happened later at higher strain as we increase the strain rate. And we see that both the attenuation and the velocity are very much dependent on the moment at which this dynamic phenomena occurs. So here it's again a proof that this system can capture dynamic processes. So finally, I'd like to show this here. It's like a conventional thermomechanical control process where you have whole lots of phenomena which occur in the steel. At high temperature there would be austenite grain growth. Intermediate temperature during the stage of hot rolling there would be dynamic phenomena. During the cooling there would be an austenite decomposition. And finally after a cold rolling you could have a post-annealing in which the recrystallization would occur. And so LUMET can monitor most of those phenomena and so can accelerate the development of model for the development of advanced steel. The LUMET system is a collaboration of many different organizations. I would like to thank the University of British Columbia, the National Research Council of Canada, TECNAR and DSI for bringing this technology to life. And thank you for your time and interest. I hope after this presentation you have a much better idea of the potential of LUMET and its potential application for metallurgical studies. If you have any question and would like additional information, please feel free to contact me at thomas@citom.org.